Here's a question. What happens when you pull a spring twice as far to start it oscillating? Let's find out. Let's take a look at a system consisting of a hanging spring with a mass attached. The animation here doesn't show the motion of the spring. I'm learning animation, but I'm not there yet with the spring. You can see the oscillation of the mass up and down. We can trace out the position and velocity of this object as it moves up and down. We plot this on a graph with the time on the independent axis and the displacement on the dependent axis. Since the displacement and velocity have different units, I place the speed on the secondary axis. The time for one cycle is the period. The maximum displacement is the amplitude. Because of when we started the cycle, the position can be represented by the equation x equals a cosine omega t. The corresponding velocity can be represented by v equals negative a omega sine omega t. For this setup, we have a spring hanging from a support. The spring has a spring constant of k. When we hang the mass from this spring, it will eventually come to rest at the equilibrium position. This is where the force of gravity is balanced against the spring force. To make our lives a little easier, we set this location to be x equals 0. Note that you could also call the position variable y if you like. Once we set the object in motion, the stretch of the spring will cause the spring force to vary. Notice that the spring force always points up and the gravitational force stays constant. The displacement is represented by delta x, but we can write it as just x because we are always measuring the displacement from x equals 0. This could be positive or negative depending on whether we are above or below the equilibrium point. The potential energy is given by U equals 1/2 kx squared. The kinetic energy is given by k equals 1/2 mv squared. Now using the potential energy equation and the x equals equation, we can see that U equals 1/2 k times the quantity a cosine omega t quantity squared. Working through the square, we get U equals 1/2 k a squared cosine squared of omega t. The kinetic energy equation and the velocity equation can be combined to give k equals 1/2 m times the quantity negative a omega sine omega t quantity squared. Again, working through the square, we get k equals 1/2 a squared times omega squared times sine squared of omega t. Comparing the potential and kinetic energy equation shows us that these are very similar looking. Note that the sine and cosine could be switched depending on when we start measuring the variables. What about the maximum energies for these? Note that the cosine function has a maximum of positive 1. Therefore, the maximum potential energy, Umax, can be written as 1/2 Ka squared. Similarly, the maximum of the sine function is also 1, so the maximum kinetic energy, Kmax, can be written as 1/2 m omega squared a squared. Now we make use of the fact that omega can be written as the square root of the fraction k over m. Popping this into m omega squared from the maximum kinetic energy, we see that m times the square of the square root of k over m equals m times k over m, ultimately being equal to just k by itself. Thus, the maximum kinetic energy is Kmax equals 1/2 Ka squared. Note that the maximum potential energy and the maximum kinetic energy are the same. Let's look at these energies as a function of position. Starting from the maximum negative displacement, where the spring is stretched the most, the potential energy is a maximum, drops to 0 at the equilibrium position, x equals 0, then quickly increases again to the maximum. The kinetic energy is a flipped image of this. At the maximum negative displacement, the object is stopped, so its kinetic energy is 0. As it moves back towards equilibrium, it speeds up, reaching a maximum speed and kinetic energy at x equals 0. It then slows down as it reaches the maximum positive displacement. Note that if you add the instantaneous potential energy to the instantaneous kinetic energy, you get a constant energy equal to the maximum energy given by 1/2 Ka squared. To help see this, remember that the sine squared theta plus cosine squared theta equals 1. Each energy has one of the trig functions. Now let's look at how the energy scales with the amplitude. We have E equals 1/2 Ka squared. Thus, the energy depends on the square of the amplitude. I've written in subscripts of 1 on the energy and amplitude to represent the first situation. If we double the amplitude, we have A2 equals 2 times A1. The second energy, E2, then equals 1/2 k A2 squared. Putting in the amplitude in terms of A1, we have E2 equals 1/2 k times the quantity 2 times A1 quantity squared. Putting through the square and rearranging slightly gives us 4 times 1/2 k A1 squared. We can see then that doubling the amplitude quadruples the energy. That means that it takes a lot more energy to get this thing moving or stopped when we double the amplitude. Think to yourself what would happen if we tripled the amplitude. Here's another video you might find helpful.